And we're back and better than ever in 17-4, where we're dealing with calculating heats of a reaction. In the last podcast, we took a look at Hess's law and how if you add up a series of reactions, the heat of reaction for that final equation will simply be the sum of all of the delta H's for all the individual steps, and we went over an example of that. In this podcast, we're going to take a look at how we can streamline that just a little bit by having what are called standard heats of formation. And so that's what we're working with right now, our standard heats of formation. The standard heat of formation is given the symbol delta H. We put like a little zero up there. That's not. That's for a standard condition. Anytime you have an O or a zero there as the exponent, that's standard conditions. And we're going to put a lowercase f down there for formation. And all this is the change in enthalpy that accompanies that's an O right there, accompanies the formation of 1 mole of substance or of a compound from its elements with all of those substances in their standard states. Which would be at 25 degrees Celsius, 1 atmosphere of pressure. All right. And so if we look at this table of standard heats of formation, what does this mean? We'll leave it right there in case you're still catching up. What this means is, say for aluminum oxide, the standard heat of formation is a negative 1676 kilojoules per mole. What that means is for every 1 mole of this thing is formed from 2 moles of aluminum. Now aluminum is a solid at room temperature and pressure. And then you have to react that with oxygen, O2, which is a gas at room temperature and pressure. And to balance this equation, because we are only forming 1 mole of substance, this would have to be a 3/2 out in front of the oxygen to balance. But the bottom line is that you're forming 1 mole of substance from its elements in its standard state. Now notice, if you look at pure elements, bromine is a liquid in its standard state. So it doesn't take any energy to form bromine from its standard state because it's already in its standard state. As is carbon in the graphite form, as is iodine in the solid form, as is oxygen in the gaseous form, nitrogen in the gaseous form. Those are all pure elements already in their standard state, so you can't form them. There's no change. However, if you change the what they look like, for example, as a diamond, in order to change carbon as a graphite to carbon as a diamond, it's going to require 1.9 kilojoules per mole of diamond formed. If you want to go from iodine solid to iodine gas, it's going to require 62.4 kilojoules of energy per mole of I2 gas formed. So let's just go ahead and show you why this is useful, and then in the last sample I'm going to show you why it works. Here's the equation. If you want to calculate what is called the standard heat of reaction, which by definition will imply everything in its standard states, it's just the enthalpies of formation of the products minus, I'm not quite sure why there's a plus sign here. This should be a minus sign for sure. Minus the reactants. Alright, so let's go ahead and take a look at this practice problem and show you how it works. It says to calculate the standard heat of reaction for the reaction of 2 moles of CO gas, carbon monoxide, with 1 mole of oxygen to form 2 moles of carbon dioxide gas. So the reaction is going to look something like this, where you have 2 COs reacting with O2 to form two CO2s. The delta H for this reaction is going to equal all the delta H's of the products, which is just CO2. And you're going to subtract out all of the delta H's of formation of the reactants. So this would be of carbon monoxide, and then we also have the delta H of formation for the oxygen. Alright? And so when you perform that calculation, let's start with the CO2. As you go up here, the formation of the CO2 is a negative 393.5 kilojoules per mole. That's for 1 mole. However, we are actually forming 2 moles. So we're going to have 2 times the negative 393.5 because you are forming 2 moles. That value up in the table is only for 1 mole. Now we're going to subtract out everything with the reactants. Well, the carbon monoxide is a negative 110.5. So you have a negative 110.5, but once again you have 2 of them, so you got to put a 2 out front, plus the formation of the oxygen. Oxygen it's a gas. It's already in standard state, so that's a 0. And so now all we need to do is have 2 times the negative 393.5 minus 2 times the negative 110.5. And it looks like we get a negative 566. So if we run this reaction 1 mole times in this direction, it's going to release a total of 566 kilojoules. Okay? Now in the next practice problem, which we're going to tackle in the next podcast, I'm going to walk through and show you why this equation actually works. And actually, before we do that, let's just make a little adjustment here. Some people we'll write this as so. If you want this a little more accurate, it is going to be the sum of the delta H of the products, and they'll also put the an N for the number of moles in front of that, and that's going to be minus the sum of the delta H of formations of the reactants. And they'll put an N in front of that as well, so that you know you have to multiply by the number of moles in front of it. Okay? We'll see you next time, and we'll actually explain why this works.